Now we're on to multi-group confirmatory factor analysis, and we're going to run through an example. And the data set that you have also would allow you to complete a second example if you'd like. But what we're going to do is look at the resiliency scale. But first let me talk about how this works in Lavaan and cover equality constraints and sort of a warning if you have watched some of my videos before. So what we have to do with a multi-group analysis is first cover the whole shebang, all one big thing, then cover each group separately, and then stack them together. So when we start to stack or nest or make data into pancakes, if you remember the lecture, we have to find a way to set groups equal to each other. Because the purpose of multi-group analysis is to start the most free and let everybody do whatever they want, and then slowly bring them together to see if they're actually doing the same things. So what we've talked about before is setting our paths equal to each other. So what happens in a multi-group analysis is that we're going to set path number 1 for group 1 and group 2 to be equal. Before we did that by creating a latent variable, so here I've called it cheese, it predicts feta and Swiss. And so if I wanted to set those two loadings to be equal, I would multiply them by the same letter. Any word is possible, but just not a word that's in the data set. And so this would know to set them both to A. And what it would do is take the paths that it estimated for those and average them together. So they'd be estimated at the same value. That's considered an equality constraint. We're forcing them to be equal. But one issue is when you're doing groups, they're sort of layered. And I can't say like women 1 equals men 1 because that would take forever. Because we're talking about the structure is the same, the intercepts are the same, the loadings and the variances. So that would be a lot of typing. Instead, there is a command, group.equal. And so group.equal says which group do you want to, how do you want to set them, what do you want to set to be the same? Sorry, not how, but what. So we can include intercepts or variances, and that's part of the sem or CFA function. So here's the list of options for group.equal, and you can actually run all of these at once if you wanted to. So the word loadings is for manifest variables. That's the loading that they get to their latent variable. We have intercepts for manifest variables. Means is for latents. Remember that intercepts in a manifest variable is the mean of it. Residuals for manifest variables. Residual covariances for manifest variables. LV variances for latents. LV covariances for latents. And regressions, which is for manifest variables. So there are a lot of options here, and we'll talk about how these pop up in a second. But sort of, much to my surprise, in a year's time, I shouldn't be too surprised that R has changed, but in a way that made these notes a little superfluous. If I was to do multi-group testing the way that I had it previously learned, is we would do each step. We'd do configural, then we'd do metric, then scalar, and then strict. And we would do each model separately and add group equalities as we went. However, there's a fairly new thing called semTools, so you will want to install that library. And you can do all the steps at once with one function, which is woohoo! That's exciting because it's quicker to code. But what I'm going to do in this lecture is talk about what line of code is actually running in the background. So it's automating things for you. But if it breaks, I don't mean this in the way of like the groups are unequal. If it like blows up, you'll have at least the code that it was running, so you would know how to do it separately. So the example we're going to walk through is the RS14. It's a resiliency scale of 14 questions by Wagnald. And this is actually from a paper that we've got published about 2 samples on resiliency. And so it's a one-factor model to kind of start easy and work our way into more complicated models. And in this example, we're going to walk through gender. So we're going to compare men to women. But we could also look at ethnicity or race and compare black to white. We did both in that paper. And I'd recommend you trying this men to women, walking through it with me, and then try it on your own with black to white. You should get fairly similar results. The items are different, but it should show you a similar pattern. Just if you want to try one on your own. All right, so we're going to program the overall model and make sure that the measurement model even runs at all. Because if it doesn't run at all, maybe multi-group analysis is not appropriate. But we're going to add something to that model. So what we're adding is a line of code that says mean structure equals true. Because everything we've been doing has been covariances model, and this is a means and intercepts model, or covariances and means. And so I need to add mean structure to my estimations. So we are going to lose degrees of freedom by adding in these intercepts and latent means, but that's the purpose of this analysis, so that's okay. And generally you have pretty complex models, lots of items, and so you don't really run out of degrees of freedom. And the measurement invariance function uses mean structure equals true. It's running CFAs in the background for you, so it can be a little slow, in our speak, a little slow. And so I don't want to program an overall model that does not include mean structure to then compare it to models that do include mean structure. So we're going to turn that on from the start to make sure that there are no bad parameters from the very beginning. So we're going to import that file, run the model, and interpret it. So in this one, you need all of the data, or at least 2 separate covariance tables, one for each group, to make it run. And I can't ever make that work correctly. So I would say in this case, you really need all the data. And another thing that you have to make sure is that your grouping variable is factored and doesn't have extra things. We're going to do this with very simple 2-group analyses. You can do more, but it gets real complex real fast, and I don't recommend it. So we're going to build a 1-factor CFA, and it should be a good model. And we expect fit to get worse as we go, because we're going to split the data set up into groups, and then we're going to force it to be the constraints. We're going to kind of compress it and make sure it matches for both groups. So we really need to start with a good model, because we know it's going to get worse as we go. All right, so I'm going to turn on Lavaan and semplot. We're only really going to make one plot with this. The plots aren't really that helpful in this particular example. All right, so we're gonna, I'm gonna set my working directory to where I have this file hidden, and I'm gonna import the file and call it data. So I have my multi-group resiliency scale. It's got 3 columns: sex, race test, and ethnicity. If you're interested in the ethnicity one, use the race test variable that collapses groups in a usable way. And then I have all of my questions. So RS1 through 14. But I'm going to examine my sex variable, and it's not factored. It imported as an integer, so I need to fix that. And it's got this other category, or none, that I need to get rid of because I can't clearly compare to one person. So I'm going to subset out that 3. So now, if I look at my table, I just have 2 of them, and they're fairly evenly split, so that's nice. I'm not comparing 50 in one and 300 in the other. And remember, you have to have at least 100 people in each subsample. Right. And then we're going to factor that variable using the factor command to add labels. And then now I have the variable is factored, it has labels, and it is what I expect it to be, only 2 groups. So this model, the CFA, is one variable. Resiliency is predicted by all these questions. So that's a really pretty simple model, measurement model. And I'm going to run that the way I've been running these models the entire time. So model name, data equals data. And now mean structure equals true. And it gives me this little warning, found more than one class model, that's fine. If I did it like this, that's when it stops giving the error. But you can, as long as you put the model first, you'll be fine. And the next thing I want to look at is summary. So let's look at how well this model worked. So my variances are positive. My R-squareds are less than 1, so no Haywood cases. Let's come up here. if I look at my standardized all, these all look very strongly on their latent variable. And I do have this new fancy intercepts section, so that's new. We don't normally have that. We normally just have variances. And the intercepts are basically the average start point for each of those questions. So it does set the intercept of the latent variable to 0. And that is basically, it's kind of a standardized thing. And so I can see, without even actually running descriptives, what the average would be for those questions. And it's about what you'd expect on a 7-item scale. So 1 to 7, some are a little high, some are a little low, but in general they're hovering around 4, 4.5. So this model looks pretty good. Let's look at the fit indices. Scroll up here. So our CFI is in the good range, or TLI is also good. RIMC is acceptable. The confidence interval is below acceptable as well. And SRMR is good. So, pretty good model to start. And then I included the fit indices here, and I made a graph. So, not a graph, a picture. Let me skip all this blah, go down here to the picture. And so what's happening in this picture, you'll see, and this is the standardized one because it's a little easier to read. I get this little triangle out here. So what is a little triangle? Well, the little triangle is the intercept. So that's how we're going to denote intercepts. So here are the intercepts in the completely standardized version. And so it sets the intercept for this one to be 0 because it's standardized in this one. And a standardized equation has a mean of 0. It's like a z-score. But it looks pretty good. Our model worked great. So let's do the next step. Make it a little bigger. So the next piece of the equation is to separate groups into their smaller subsamples and test them separately. And what that does is it allows me to see if the factor structure is probably the same. So if one of them is good and the other one is poor, then this would be a place that you would stop and say, well, the model totally fits for one group and is a hot mess for the other group, and talk about why. And so to me, this step really just helps make sure that when you do the nesting, the configural step, that this is going to work. And then they should look roughly equal. So I'm going to subset that data. So I'm here under separate group models. So I subset men into one group and women into another group. And then I'm going to run, and all I'm doing is changing here the name of the data set that I'm using. So for men, let's see what happens. So no Haywood cases, it looks like. If I scroll up, they all look pretty strong. And then the the intercepts are all in the 3s and 4s. Let's look at fit. Fit's 0.92, 0.91, good, stayed about the same. Our MC went up a little bit. And my SRMR stayed about the same. Now let's try women. And if any of this was poor, I would look through residuals, fit, modification indices, just to see what it would suggest. Okay. Now I can make a picture of this, but the picture does not change. So it doesn't even look like anything happened over here. The only thing that's really changing is the numbers on the graph, because the picture shouldn't change. So it's kind of a check to make sure you didn't screw something up. The model isn't changing. The group, the people you're estimating for is. So let me try women now. Okay. No Haywood cases, looking good. If I scroll up here to fit, women fit a little poorer than men. So 0.9 if I round up, 0.88. Excuse me. RIMC's okay. SRMR is good. But there's no particular reason why the women one is slightly worse. Maybe it's because some of the loadings aren't as strong. Maybe it's just a little more variance in the women. And you'll see once we get going that this isn't a huge difference, and you'll see where this breaks and maybe why this difference occurs. But me looking at this, I would say they're about the same. And I can't really compare chi-squares because they have the same degrees of freedom because they're the exact same model. I could compare AIC and ECVI, but the purpose is not to pick the better model. It's to show that these models are roughly equal So I can start to group them together and maybe see where the roughly equal ends and they stop being equal. So we don't know if this is a significant difference in fit, although my CFI looks like it would be more than 0.01. We don't really know where it's a significant difference in fit until we combine them together. Okay? So that's kind of the start, and it's really just to make sure that everything that you're trying to do is going to work. In the sense that if for women 3 of the loadings didn't even load, and for men they're all perfect, that's a good sign that the models do not have the same configuration. Okay, so running configural won't help. So what I'm going to do in this step is tell you how to run the measurement invariance function, and then I'm going to walk through what it's doing in the background. So I run measurement invariance here. You can capitalize this I if you'd like. That's the same function. So you put the model in first, comma, data equals data. Now in this one, be sure you go back to the big data set that has everyone in it. Because the next line, group equals, is going to pull the group on the 2 separate samples into one model and stack them together. And so this here would say sex because that's the name of the column. But be sure this data set is the combined data set and not the separate data sets, or this won't work. And we are talking about doing steps by using Brown steps by including strict. Some people do not include it, but we're going to talk about including it because it's easier to tell you about it and let you know about it, and then you can exclude it if you want, rather than somebody surprising you and you're going, I never learned that. So we're going to say strict equals true to make sure that step gets included. So when I run this, let me come over here. I'm going to skip all this. So I'm going to open up semTools. You will want to turn off scientific notation at this point for reasons you'll see in a little bit, but the numbers get very tiny and you will want to be able to see them. And if you're not good at scientific notation, this is where it would help if they're off. Okay, and that's the line that turns them off. Okay. So I'm going to save this. Multi-steps equals measurement invariance. Here's my model name, the original data set, the group name, and I said strict equals true. Now this is automatically going to print some stuff out for me. And what it does, and this is one thing I don't particularly love about the way this works, but it is a fantastic function. So one thing it's going to do is it uses what it's changing. So it includes latent means without us asking, but we can always ignore it if we don't want it. It tells you what constraint it's adding. So I've got configural, loadings, intercepts, residuals, but does not use the names of the steps. So we talked about it as configural, metric, scalar, and strict. And so it uses the names of the actual piece that it's adding. But in a later step, when we're testing for partial invariance, it uses the names of the real, step. So I have that here on line 98, metric, scalar, strict, means. And so it kind of mixes and matches terminology, which to me was a little confusing. So I wish they'd pick one and stick with it, but here's how it's going, just so you know. Okay. It shows me, and I didn't copy this output because we're not going to use it, but it shows me AIC and BIC, chi-square, and then a chi-square difference test going down by model. Now, chi-square difference test is notoriously oversensitive, and you will see here that several steps are significant, but the CFI does not match. So we're actually going to ignore that and focus here on the bottom where it says fit measures. Okay, and that's what I copied and stuck in here. Now I can interpret directly from here, but what I'm going to do over the next couple of slides is talk about what this function is actually doing for you, so you can kind of see what all the work is that's going on in the background. And then at the end we'll talk about how you can pull the models that it ran out separately so you can get all the information you need for publication. Okay. So we're going to come back to this chart here in a minute. So what happens with configural invariance is that it takes the models and combines them together and looks at to see if they have the same factor structure. So this is basically, are they both pancakes or is one of them a crepe? Okay. And what's happening in the background is if I were to run this as a regular CFA, I would do CFA, my model, data equals data, mean structure equals true. That's all the things that we've just did for our overall model. And I would only add group equals sex. So that's the first model, is to have within a CFA a group term. And so it does that for me automatically when I told it what group it was. But that's the line of code that I could run to get this exact same step. Oop. Go this way. So for configural invariance, if I were to write out all the fit indices, which again, I'll show you how to get these at the end, we have pretty good fit. And so it's kind of an average of the men and women's fit. If you look at the numbers for men and women and then look here, it's not totally an average, it's kind of a weighted average. But it looks pretty good, actually. It's within the range of good numbers. So, huzzah. We don't compare configural to anything else. We're just trying to make sure it didn't blow up. And it doesn't look like it blew up. So, if the fit were to drop significantly from the overall model, that is where you'd say, well, okay, this didn't work. For metric invariance, what we're doing is setting the loadings equal across groups. So metric, remember, is loadings. And what's happening, is I have that same CFA code, data equals data, mean structure group, comma, group.equal equals loadings. So we're told it to just now add the loadings to get to it. And what it does is it sets those loadings across groups. And so I cut and paste just a little bit of the output that you're going to see in this step. And so the first one is the marker variable, so it ignored it. But you see the little number here, and the little number, P2, P3, P4, corresponds to a loading that is set to equal. So it forced the RS2 to be equal from men to women. And we'll look at this a little bit more when we talk about how you get all of the output out of this, but this is the line of code that it's running for you. Now with metric invariance, if I pull the numbers out, it looks pretty good. The fit doesn't really seem to drop too much, and there's no real change here in CFI, and so they're not different. Woohoo! That means that when I added the loadings are the same for both groups. So with configural invariance, the picture is the same for men and women. With metric invariance, the loadings, the relationship between the factor and its items are the same between men and women. The next step is to add strict invariance, scalar invariance, which is where we're going to set our intercepts to equal. So we're adding intercepts to our group.equal code. Now remember, you're not actually running this, I'm just telling you how it's run. And what we're doing is making the model more restrictive. And so I've got group.equal, all of this stayed the same from the previous slide. Now I have loadings and intercepts. So we're adding constraints, not changing them out, adding them. So we're getting more and more restrictive. And what we can do is see that here, when I get to intercepts, they get little numbers here. And Lavaan does this automatically for you. But that anytime you see this next to it, that means it's set them to be equal. And so between groups, they are equal things. And I'll prove to you that it actually does this here in a minute. Okay. So with scalar invariance, if I am using my delta CFI rule, it's changing 0.007 if I subtract the two. That is not greater than 0.01, so it's less than 0.01, so it's not significantly different. Now the fit is getting worse. So you can see here that RIMC is not really changing because complexity-wise it's changing. And so because it has that penalty for complexity, it's sort of evening out. So the fit is getting better, but it's getting more complex. Anyway, or other way. Fit is getting worse and it's getting less complex because more constrained models are less complex. Because if I'm estimating, saying all these things are equal, that's less complex than letting them be separate. Sorry. So I don't have a significant change. So we're still good. Everything is still invariant, which means it's not different. So this is sort of a weird analysis in the sense that you want things to be not different, but when they're not, that's also cool too. The last piece that we're going to run, and then we're going to talk about latent means in a slightly different way, is add the residuals. So a lot of people leave this out because you just can't meet it because often scalar invariance doesn't work. But for me, strict invariance is really interesting because it implies a difference in selection on a scale. So for one of these, what we found was that the averages were all the same. So the averages were the same, and the loadings were the same, and the latent means were the same. But the pathway to that was what was different. So for I think whites, what happens is they're picking 4 and they're picking 3 to 5. But for blacks, what's happening is they're still picking 4 on average, but they're picking the entire range of the scale, so 1 to 7. So having that wider range is really interesting. It's actually an issue of heterogeneity. But also, like, why is that happening? So what is this other variable that might explain to us why some participants pick all right together and some participants pick farther apart? That maybe isn't due to sample size. So to add residuals, you do loadings, intercepts, and residuals out here. And what we see when we add that model is that it is significantly different. So I'm subtracting going down here. So 902 to 888 is a significant change. And so that implies that the model did not fit well by adding those constraints. Okay. So back to that output that we saw earlier, what I would do here is go to this CFI delta. So the numbers are just slightly different than what I found. They're here, they're the same, but the subtraction, it does more decimals than I did. So that's kind of nice because it gives me more precision. So with this first one, there's nothing to compare to, so it says NA. The loadings one is not significant, this one is not significant, and residuals is. So fit.residuals is bad, which is the strict step. And so just kind of a warning that this also runs latent means, which I'm going to ignore at the moment, but if you want to do latent means this way, it's right there on the thing. Okay. But this is the step that broke, so I'm going to ignore means either way. Because I got to fix this step first. Okay. Remember that the rule is less than 0.01 is okay, greater than 0.01 is not. So what now? Now we're going to do partial invariance. And to me, this is where semTools really shines, because the way to do this before, if you watch some of my old examples, it took a little bit of work, and I think the way they've coded partial invariance is very nice. So what it's going to do is we're going to figure out which items we can let free. So we've been restricting and restricting and restricting. So we said, okay, the picture has to be the same. Okay, now the loadings have to be the same, the means have to be the same, and now the residuals have to be the same. So at this point, everything is being forced to equal. Well, not everything, but close. By forcing those things to be equal, it broke. So let's let some of them not be equal and be like chill about it, right? So, okay, fine. Not all of them have to be exactly equal. All right, well, but which one, where do we start? So what partial invariance does is, to me, it's like trying to figure out which light switch goes to which light in your house, which if you've been in my house is like a difficult adventure because there are just light switches freaking everywhere, and sometimes you just don't know what they do. So what you do is you stand around the house and somebody flips one on and off until you find the light that's turning on, right? Same idea. It takes each loading or each piece, in this case they're residuals, and turns them on and off, on and off, on and off. And it shows you how much you gain in fit or lose in fit by letting it be free. And so it kind of, it tells you exactly how much you would gain by letting that path be relaxed or not constrained. So they're not equal to each other anymore. Okay. So we're going to use partial invariance, but you want to do that in the step that you broke down. So if I broke down on the side of the road, you don't want to come to my house to fix my car. You're going to come to the side of the road, hopefully. So we're going to look at the residual step here. And this is where the mixing and matching of terminology, I think, is unfortunate. So what we're going to do is figure out what level I need. So metric is for the loadings, and the little code piece is going to look like this. Scalars for intercepts, and this is how scalar is written. Strict is for variances, and it's got double tildes. That only is going to matter here in a second. So what we're going to do is we're going to let partial invariance figure it out for us. Woohoo, party! This is the slow step. So we're going to take that saved multigroup fit, and then type equals literally the word type, and we'll type in the step that broke. And so it's either metric, scalar, or strict. The equality constraints are labeled loadings, intercepts, and variances, but here type needs to be metric, scalar, or strict. So let's try that. That is here. I'm on line 107. No, I lied to you. I am here on 100. Yes. So I've got multi-steps because that's the first time I ran the multi-step invariance. And I broke down as strict. And this is the thing that's just a touch slow. Because what it's doing is it's running the model with parameter 1 free, turn that back off. With parameter 2 free, turn that back off. 3, 4, 5. So if you have a lot of parameters, it's probably going to be pretty slow. Now, what partial gives me, I'm just going to type it down here, is a bunch of output. Just like gobs and gobs of like stuff, which is kind of nice because then you can see like, look at all this crap. Oh my God. But not what I don't care. I want to see what I need to see to figure out what is the important thing to let go. So what I'm going to do is run this strict free here. I'm going to say my partial step $ results. So that's only going to give me the tests of invariance. And I'm going to come over here and click on it. And now what I have is a sortable table, which is a little easier than running code. And if you're using Studio, you should be able to sort them. So you're going to click on it over here, click on free CFI, because that's the parameter we're using to determine which models are good and which ones if it's getting better or not. And just sort it. You want it to be negative because that means that it's kind of reverse coded. It means that the chi-square is going to go up 0.003. Okay. Plus, we're interested in what happens when I free this. Well, what happens when you free that parameter and then go back is that the fit drops 3 points. So that's what's happening. It's saying free minus fixed, and then we're losing 3 points by fixing it. Okay. All right. There are other ways to look at this. We could look at chi-square, but look, they agree. And since CFI is our criteria, let's focus on that. So what I can do here is I just copy this. So it's RS9, that's the problem. You see how it has the double squiggles? That's the residual variances. It's a little weird. It says residual variance with itself, but what we're saying is like allow men and women to be different on this one. So you would copy that code exactly, come back over here, and then let me go back to my slides here. So this is where I talk about sorting them. So we're going to pick the largest one, and the problem is the constraint. The problem is that we force them to be equal and we shouldn't, so we're going to let them go free and do whatever they want. Okay. This is like letting teenagers go drive. I don't know. I don't have a good example for that. So we're going to use group.partial. So group.partial is, okay, we have groups, but they're only partially invariant, so let these things do whatever they want. Okay. That function works in CFA and measurement invariance. Okay. And this is actually going to be super sweet, but I'm going to explain why in a minute. You could do more than one, but I'm really going to force you guys to do one at a time just to make sure it works like you think it works. And so you pick the largest one first and then work your way down. Alright, so here's my partial strict 2. So I'm on partial invariance on the strict step 2. Oop, no, here, step 1. Partial strict 1. I've got my model, my data, group, strict equals true, group.partial equals, and I cut and pasted this here with the double squiggles directly from here. Okay. So let's run that. So now it gave us a new set of fit indices. And not quite there yet. Wait, where's my fit slide? Okay. We'll hold a thought on that slide in a second. So with the RS9 free, I included my previous one. So one bad thing is that it deletes the previous step. So I don't like that so much. But if I look, I had 0.888. I came up to 0.891. So I got 0.003 back. So that's what that number means in the partial invariance results. It's still significantly worse than scalar. So I'm still comparing it to intercepts here, and it's 0.012 or 0.011 if we were rounding, and that's still not good enough. I need at least probably one more question. Now when we get to looking at the output for these models, where we can look at all the loadings and residuals, here's what happens. The little number goes away. So you see we had these little numbers before which indicated that they were the same. So if you look at RS8 here, it's 1.9 and 1.9, so they're literally forced to be exactly the same. So something interesting, the fully standardized model, they're not, which is kind of fun. But anyway, the loadings are forced to be the same, but here, RS9, they're not. So the way I think about partial invariance is if essentially with with invariance testing, when I'm doing my steps down, they're kind of like ANOVA. It's like, was it significant? Nope, moving on. Was it significant? Nope, moving on. And then partial invariance is the t-tests. Where is that significant? So let's run all of them. And here's the one that's significant. Let's fix it. That's not quite how you would want null hypothesis testing to really go, but it's kind of the same idea. Okay, so we talked about this. It's still bad. So we didn't come up with enough CFI to find partial invariance, so we really need to do another one. So let's find another one. So what I did was I ran partial invariance on this model, so not on the overall model, on the partial strict model. Wait. Okay, I'm going to save my results again, click on strict free, sort CFI, and it's RS13. Okay, this isn't really going to change too much from the previous model because they're tested independently of each other, so that was actually the next one down before. I'm going to cut and paste RS13, and I've added it. So here's partial strict 2. I still have RS9. Now add RS13. So that's the theme of this lecture, is that we're adding constraints as we go, not replacing. And then we're adding, loosening those up. So we add them to each other as opposed to trade them out. So let's run that. Okay. And I have that on a slide here. So now I have both of these parameters are free, and what you'll notice for women, they have a wider range. So it's 2.07 versus 1.23, so it's almost double the variance for women than for men. And so these are residual variances, so it's the spread, it's the standard error basically, or standard deviation around the mean. And so women are endorsing a much wider range of answers than men on these two particular questions. If I look at my output I got here, I just cut and pasted it over here, I can stop. So I'm at 0.009, but that is less than 0.01, so we are good. And on mine I included both steps at once, so I could compare. I got another 0.003 back. Okay. So I would stop. Okay. And one thing about this that I was asked, like, when do you stop? Well, you stop when you either get to straight or partial invariance. So this would be partially invariant except for 2 items. But it's a really hard thing to know how many items is okay because this is only 14 items. So 2 out of 14 is, I think it's 14. 2 out of 14 is 14% of the scale is not invariant. So I would suggest sticking with a smaller number. I think if you told me 1/3 of the items weren't invariant and asked me to believe that the scale was the same for all groups, it would be a little, I wouldn't probably believe you, but there are no real rules for this. Definitely at half you're talking about, these participants are taking them at this scale in a different way, but I don't know that there is, that I've seen that there is a rule about how many items you can release and still consider it partially invariant or still close enough to similar. So this is just a careful interpretation. So you don't release all of them, you just do them one at a time, and you do them in order of worst item to slowly getting better. So the interpretation here. So how do I make sense of all of this? So the resiliency scale is mostly invariant. The structure is the same, the loadings are the same, the intercepts are the same. So that's a big chunk of the model is the same. And most of those error variances are the same across men and women. 2 items show differences in variances, 13 and 9, where women show much higher variances than men. They have the same mean, but the spread is different, right? So one of them is more kurtotic than the other. And those 2 items, by the way, are I keep interested in things and my life has meaning, where women endorse a much larger range of things than men. Men endorse right in the middle and very close to the middle. Women endorse kind of right in the middle and a little bit bigger of a spread. So how do I get the numbers for each step? So how can I look at those parameters that you've been showing me this whole time? And how do I get more of the fit indices from each one? Because maybe I need to also include SRMR because my instructor is making me, or just any other thing I want to look at, like Haywood cases. Now the cool thing is when you run the measurement invariance code, that one line of code actually runs all those models in the background and saves it. So if your computer is struggling, this is going to be kind of a big analysis. It's not huge, but don't have like 600 things open. And so what you can do is pull them out. So what I have here, on a side note, is I've saved them all separately because the way that they're stored, they're not hard to get to. It's just you can't pull them in a nice clean way like you're used to. So I'm going to save them separately. So I'm going to save my configural step as partial strict 2. So I picked the very last step that I stopped at. And it's $fit dot, and then there's configural. Now if I run a summary of that, I have all the loadings, all the fit indices, and now at this point I could also do modification indices or fit measures. Okay. That is essentially pulling out that whole CFA that we talked about. So it saves all the CFAs in the background for you, so you don't have to run them separately if you want some more information from them. So that's where I got SRMR from. Brain fart. So let's look at this summary one more time. So here's something fun that happens when you get these. It gives you the overall fit for the model, but it only shows you, and when you do these grouped analyses with CFA, it only shows you chi-square. It does not actually show you SRMR and RIMC and CFI. You have to use fit measures to find those. But then it shows you, here's women. And it, like, see, there are no little numbers here because we're allowing them to be different. So here's men. So for RS2, I got 1.19. For women, I got 1.29. So they are allowing them to be different. Okay. And so it shows me all the loadings for those 2 groups. I can look at metric here. And this is where I started to get the pictures where I had pulled, there were the little loading things pop up. So here RS2 is 1.232. Down here for men, same thing, 1.232. So what's happening is it's forcing those to be the same. If I look at scalar here, it's going to separate them out. And now I've got my loadings and my intercepts are forced to be the same. And this to me is the coolest part. When I run residuals here, since I ran this on the last step, it has the blanks. So it only released them in the step that it was supposed to and not the entire time. Additionally, it sort of remembered to let them be free. So this is where I knew what those variances were. So you're going to have to run this code to be able to see, you can pull the items that you're interested in, but to be able to see where and what the loadings actually were that were the problem, you're going to have to separate out the different CFAs to be able to find what loading actually it was. So I know it was 9. Now what is the actual number for it? Well, it's 2.06 for women versus 1.2 for men. Alright, so you're going to have to pull those to be able to view the numbers. Okay, so moving on to latent means. So latent means I could do by just looking at the last line of code that we had. It's very clear that they're not significantly different. Let me scroll up here to this last one. So fit.means, look, there's no difference in CFI, so they are not different. But the issue is, let's say you want to use those weighted means as a predictor for something else, or we want to do t-tests to determine if they're different. Let's look at some effect sizes. And then this slide's directly lifted from the previous notes. And this is just a really push for the idea of weighted score, because weighted scores are much more interesting because they're weighted. They're using the amount that they contribute to each latent variable as opposed to averaging them all together, sort of ignoring that some questions are better than others. Now, the way to do this in R, please someone find an easier way because it is quite unfortunate. But like conceptually, here's what's going to happen. We're going to take those people's score on the actual question. So I wrote 7. I'm going to multiply that score times the weight for the loading and then average or total that. So you're basically taking the loadings for each item, multiplying it by what the participant actually scored on that item. So yes, they wrote a 7, but this item is only weighted at 0.5, so only got half of that score. And then we average or total that whole thing. Okay. Now this is a whole lot of matrix algebra, which if you are not familiar with, just trust me on it. Okay. So what you're going to do is take the loadings for each factor. So big warning here, if you have 2 separate factors, you need to separate those weights out into the factors for each one. So don't just average the entire shebang together. For multiplication purposes, you could multiply as long as it's everything together, as long as they're in the right order. But don't just slap it all together. Is, I guess, the answer here. So let's save those loadings. Where am I at? So here, latent means. So I'm going to pull from parameter estimates and pull the loadings from the very last step. So I pulled that from here, strict. And so let me look at those loadings. So what's in here? What it has is it has what the loading is. It has what group it is. So 1 versus 2. So for men and women, I have different things in some places. What the label is for the loading, the estimate, the standard error is the EP. So this is the output that you normally see. Okay. Now, only thing I want from that is I want to separate them by group. So here's the first one. So men are as group 1 and women is group 2. And I want the operator where it's tilde, equals tilde, and that stays the same because equals tilde is the one for loadings. And I want to select the column estimate. So this is a bunch of code, but what it does is it says, okay, I want to see group 1 and group 2 differently. I only want to pull loadings. I don't want residuals and errors and all this other stuff. I just want loadings, and it pulls this column. Okay. So, let me leave that up, and we'll see if we did this right. Okay, so let's pull men load and women load. So men load here is, I have a bunch of estimates. I have 1, 1.23, 1.06, and technically women should be approximately the same thing, right? Because we're forcing them to be the same. Let's go over here. So for 1, 1.23, 1.06, 1.23. So it pulled the men's estimates. Come down here to women. 1, 1.23, 1.06, 1.23. Okay. So it pulled men and women's loadings together. Okay. So now that I have that, that is a column of data, okay, with the loadings in them. Now what you do is you take those loadings and you multiply them by the participants' actual scores. So the big focus here is make sure you multiply the men's loadings by men. So this whole row needs to be about men, and this whole row needs to be about women. So if you remember how apply works is you put in the data set. So I'm going to use my men data set. Now why have I separated out columns? Well, if I look at the men data set, it's got 3 extra columns at the beginning. So I need to make sure I match the estimate order right, to the column order. Okay. So let me look at my min loadings here. Let me look at all of them here. So what order are they in? Well, the estimates are RS1, RS2, RS3, so they're in order, thank goodness. Okay. So they're in, if I look at right hand here, they're in this order, from 1 to 14. If I then look at the order of the data set here, they're in the same order, but I've got to ditch the first 3 columns. So that's why it's 4 to the end. Okay, so data set, columns need to be in the exact same order as your estimates. 1 here is the do this by row, not by column. And then we're making up a quick little function where we multiply a column of data by a row of data. Okay. And that's just the way, long story short, matrix algebra works. We're going to multiply a column by a row. And then that's going to do that. Repeat that for each row. Okay. So if you had to change this, what would you need to change? You would need to make sure that the columns are in the same order. So remember, you can see and then rearrange the column number order here. And you need to make sure that the data set is the group that you're pulling. If you have multiple factors, you would have to do min multiply 1 and min multiply 2. So you could actually get away with doing them all at once here, but as long as the columns are in the same order. And actually, if you're going to have multiple factors, this is where I'd separate them. So let me put a note here. Okay, so I wouldn't separate them until the very end. Here, if you have multiple factors, rearrange column order in apply. So I would look at the way the estimates were ordered by clicking on loadings. We called it loadings anyway. And if the estimates were ordered like RS1, RS4, RS6, I would here in this section put C column 4 for column, so RS1 would be column 4 in here, comma column 4 for RS4, and then column RS6. Like, I'd rearrange the order of it here so that they matched what the order is here, because otherwise you're multiplying the wrong things together. Okay, that's the most difficult part about this. Alright, so let's run those. I did that separately for men and women. And what my min multiply now has, let's look at it. Min loadings, where's my multiply here? Is it gives it to me in list format. So let me write this down here. Okay. And so what it does, which is blah, for each participant, is it gives me a column of data. It says, oh, okay, fine, here is the loadings times the row, so here is their re-estimated scores. So it took 1 times 4 and give me 4, and then it took their score times 1.23, so they put 1 here. So each person's going to have different scores. Okay. Now these are the non-standardized estimates. So one thing about this is that it will, the scores will likely go higher than the normal scale would because we're using the weights, the non-standardized weights. And remember that non-standardized weights can get bigger than 1, so that's one concern. You could also pull the standardized estimates. Anyway, so the way to get it from this weird list format to something that's usable is do as.data.frame. So now with min multiply, what I have is each column is a participant and each row is an item, which is not super helpful because it's not the way we normally think about data. So what you can do is transpose it or flip it, is the way I think about it. So go like this, and that's the T function. So now min multiply, here we go. Each column is an item, and then each row is a participant. So that just turned it on its side, which made it a little easier for us to deal with. Okay. Now if you were, let me do women as well. If you're going to have multiple factors, this is where I'd separate it out into like make columns 1 through 5, what you're interested in. Or another way to do this is to do apply again instead of using row means. So what I could do is say that my min latent equaled, latent. I could use apply here, and we would take min multiply, and I would say, okay, only columns 1, 4, 8, and 10. If that were the columns that I was interested in, and then 1 for row, and then mean. Okay. It's not totally going to like that because, there's a comma missing. There we go. And then that runs fine. Okay. So that would be, and then I could do the exact same thing if I wanted to separate it into 2. Let's just pretend. So lots of pretending going on, but so then I would use 2, 3, 4, 5, right, 6, 7, etc. And that would be a good way to separate them out. That's probably the least confusing. Okay, if you have one factor, you can also use row means. So row means will give you the entire row. You could also put the square brackets here. So sorry, I don't mean to give you so many options. I know you guys don't like that, but I could do here 1, 2, 5, 8, that sort of thing. So making it clear that if you have multiple factors, do not add them all together. Okay. So I'm going to run min latent and women latent here so that I have their scores. And then if you look at it here, let me just run it, min latent. It is every single score latent to average, since I average them together. Okay. Now you see some of these scores do get higher than the 1 to 7 scale that this runs, but that's because we use it on standardized estimates. That's fine. Now that I've done all that work, I could use it to predict another variable. I could use that in some other set of analyses that I was interested in. I could use it in a separate CFA sort of way, or path analysis. But we're just going to do a t-test. So we're going to compare group 1 versus group 2, so min latent versus women latent. Paired equals false because these are not paired together. Var.equal equals true. So it gives me a little t-test. Here's my average, my latent mean for x, my latent mean for y. So for men it's 5.52, for women it's 5.57. Yeah, that's not different, right? My t-value is not significant, so those are roughly equal. I could also grab the standard deviations from those, so they also have the same spread of data for our latent scores. And then 2 options here. If you're familiar with my effect size coding that I have shown people before, is another thing you can do is pull the length to look at how many men there are and how many women there are that have full scores. Okay. And then you can type into my independent T effect size coding. And if you're interested, the great thing about that is that it does lots of different effect sizes, and not just in Cohen's D, but there's also another little effect size plugin that we can use. So let me make sure I haven't skipped anything on here. We talked about this one. We've separated them out. Talked about this thing a little bit. This is converting from a list to a data frame. It's great. We're going to get the means for each person. You can also do row sums. And then we did a t-test for them. Alright, effect sizes. So install the F-size package. It's, I think, programmed by some people at Notre Dame, Ken Kelly. And so it is actually really awesome too. I used it to help make sure that my effect size code worked correctly. And so the code is Cohen.d, and then it gives you group 1, group 2, and the auto default is for paired equals false to be off. This gives you the traditional pooled variances on the bottom for Cohen's D. So it's a little bit quicker than my code. It also gives you the confidence interval. So the effect size difference in latent means for men and women is 0.03. That is about zilch McZilch face. So there is no significant difference between the groups, which matches our latent mean invariance test that we ran but now I have people's actual scores, and so I could use those to do something else. And for me, what I would really do is use them to predict some divergent or convergent tests to show that the scale works the way I expect it to work. Right. So now I have each person's individual score. Maybe I could correlate that with some other items. I could use it to predict depression in this case, because it should be negatively correlated with that. I could use that to see if it's better than the summed scores or total or average scores from the scale in a regular computation. So having the raw numbers by participant to me is especially useful. If your only concern is if they're different or not, do it through measurement invariance. It's much faster. But if you're wanting to use those variables, here's one way you can do it. And I think the biggest concern when you're running this code, somebody write a function, is to make sure that the estimates are in the same order here, or you've multiplied by the wrong thing. And then if you have multiple factors, don't average them all together. Alright, so that altogether is multi-group invariance testing. So you should try some of this on your own, or go watch the videos with some more examples of them for the class assignment.